Hello friends, welcome to my channel. Let's have a look at problem 79, word search. This is a very classic problem now. So in this video, we're going to explain a method or a pattern of solution, that is backtracking. First, I'll read through the problem statement to digest the requirements, and then we do the explanation and do the coding together. First, the problem statement. So here we are given a two-dimensional board which has size m by m, right? And also we are given a string called word. So we want to check if the word exists in the grid. So the word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. So the same letter cell may not be used more than once. So this is also an important constraint. So here are three examples. So in example 3, so the return is false. So we do not have A, B, C, B. Because here in example 3, there's only one B, right? But in the words, there are two B's. So we need to return false for sure. So in the first two examples, so we're going to return true. Because here in example 1, the word is A, B, C, C, E, D. So we have one A, B, C, C, E, D, right? So similarly, in example 2, the word is C. So we have C, S, E, E. So this is the main problem statement. So before we do the analysis or talk about the solution, let's also pay attention to the constraints. First, the board size, that is the length and the width, or the number of rows or number of columns, are given by m and n respectively. So they are bounded in between 1 and 6. So this basically gives us the board size. So secondly, the word length. So the word is at most length 15. So this also gives another size. So together they confine the problem size to a certain degree. So here the board and the word consist of only lowercase and uppercase English letters. So because of this assumption, actually we need to distinguish lowercase and uppercase English letters, though in our code, so this is not explicitly self-speaking, right? So with that said, let's look at the treatment. So here we are going to use backtracking. So the backtracking in some sense is very verbose. So basically we want to try to start at every position. So each of the possible position, and then we do depth first search, so to see if we can match the given word. So this is basically the rough idea. So here, before we do the coding, first let me mention one point. So this is actually a crucial one or critical one. So we shouldn't forget the backtracking operation after we try a current option. So this sentence may not be crystal clear at this point. As we do the coding, so this will be self-clear. So next, so backtracking is sort of routine in format, and essentially trying all the possibilities. In the problem here again, so we have noticed that the board size and the word length, so we could try to solve it with this method. So we're going to explain the details along with the coding below. So with that said, let's look at the coding. So here, first I'm going to make some preparations. So let's call it preparation step. So let me get the number of rows, number of columns, and the length of the word. So it's board and board 0. So the number of rows and number of columns, and then the length of the word. So because we are not allowed to visit the same letter cell twice, so we need to use a set to monitor the process to avoid repetition. So here the set will store the positions or coordinates. So you can see positions or coordinates. So anyway, so this is the first step. So the second step, so I'm going to write a DFS hyperfunction. So this hyperfunction will help check if start from certain position, we can find a substring of the word, so to speak. So let me first write down the function and then explain. So here I'm going to call this function backtrack. So we're going to accept the coordinates and the index. The index is for the word. So basically what we're going to do is here RC is the position or coordinates, and I is the current index of in word. So what we want to return, so we return a boolean. So basically check if we could find the word I onwards, starting from position RC. So this is the interpretation of this boolean function. So once we make the arguments meaning clear, we can easily write the code or the function for this backtrack function. So first, if I equals the length of the word, so basically we are checking if we can find an empty string, right? So this return true. So you can regard this as base case or a stop condition. So similarly, we want to try to check this another stop condition. So that is the position is out of bounds, or the current letter in the board does not match the letter in the word at current index, or we have visited the current position. So right. So this actually is easy to code. So if r less than 0 or r greater than or equal to m, this is for row, or column less than 0 or greater than or equal to m, right? Or the board at the current position does not match the word at the current index, or so we have visited the word, the position in visited. So in this case, so we're going to return false, right? So this is actually easy to digest. So next, let's write the main logic. So now we want, because currently we are at position RC, so we want to currently we are visiting, so we add this guy to the monitoring set. So this is standard for if you're familiar with graph or tree traversal, right? So this and then what we are going to do after we visit this, we want to look at the neighbors of this position and then move the index onwards, in other words towards the right. So basically I want to introduce this flag. We would like to look at the 4 neighbors, the 4 possible neighbors for this current position, right? So we're going to call backtrack. So r, let's say +1, c, I +1. Or let me copy this function. So let's this is r -1, and then we consider, let's see, c +1, right? Or let's see, c -1. So this is a boolean, right? So this is what we want. So as we mentioned at the very beginning, so we shouldn't forget the backtrack operation. So if we do not use this c, so actually we need to revert to the previous state. So that is, after we doing this operations here, so we need to do remove, so pop the RC position. So what we want to return is the flag. So if the flag is true, it means that starting from the current position, we can find this word piece. So otherwise we cannot. So next, so we are going to prepare the return or prepare the check. So basically, we want to check all the possible positions in the board. So this is basically very standard. So for I, let's see, for R in range M, for J in range N, right? So we want to check if we can find backtrack R. Let's use C or IJ just to be consistent. So RC. So we are going to start from index 0. If this is the case, it means that we can find the word in the board. So we are going to return true. Otherwise, if we have finished started from every possible position, we still cannot find the word. So we're going to return false. So this standard piece of code forms a solution format to this problem. So this classic problem, I would say. Before we doing any comments, let's first do a check. Yeah, it passes the first example, I guess. So now let's look at the generic case. Yeah, it passes all the cases, but it's a bit slow because here, essentially, the backtracking method is very verbose, in some sense, brute force. So here, notice that for each position, actually, we called this backtrack function. So basically, that you can have a rough idea about temp complexity. So we do m times n. Call of the backtrack function. Then we just times the temp complexity of the backtrack function, right? So for the backtrack function, so because the word length is given, right? So at each position, so we have at most 4 options. So in other words, so this guy basically has a temp complexity roughly O of 4 to the power length. So this is the word. So let me write like this. It's bounded by this this thing. So overall, the temp complexity for this is bounded, or we can write a big O, right? So if we like, so m times n times a power, let's see, 4 to the power this, right? So but you can try to do these things. So this is bounded by m times n times is the 4 to the power 16. But this one, this is bounded by 6 times 6. So up to a constant, so we need this number of operations. So here is not power, so it's multiplication. So this 4 times 16, let's see, 15, right? So 15. So you can do something like this. Estimate this number. 15 is actually 2 to the power 30, right? So 2 to the power 10, then raised to the power 3. So this is roughly, this is the 1024, right? So the 1000, 10 to the power 3. And then we have another 3, so this is 10 to the power 9, right? There's a lot of operations actually. So with that said, actually, I guess we'll gain some real feeling about this backtracking technique or method and its temp complexity. So with that said, I guess that's about it for this specific problem and this video. Thank you.